So the previous chapter we had looked at residuals. Now with this chapter we're going to focus more on those residuals and on a regression line, or also called a line of best fit, something we saw in previous chapters. So in chapter 6, 7, and 8 we learned that to examine the relationship between two quantitative variables by looking at a scatter plot. We've learned, if it's linear, to quantify the strength and direction with a correlation and a model with least squared regression. Now we will learn to apply inference, meaning conclusion and meaning, to these regression models. So now we're going to interpret what does this regression line actually tell us. We're going to develop both a hypothesis test and a confidence interval. So with that comes assumptions. Now we have some different assumptions here when we're looking at regression. The first new one is the straight enough condition. We need to check that the scatter plot of my x and y has a linear form, that it kind of roughly resembles a straight line. So, no U's, no kind of curves here. My data needs to be somewhat of a straight line. Next is independent assumption. With that comes two conditions underneath it. So the errors in the true underlying regression model must be independent from each other. We need to look at randomization. That'll help us verify independence. The data comes from a random sample of the population. And the random residuals condition. Looking at the residuals for evidence of patterns, trends, or clumping, any of which is a failure of the independent assumption. And we'll look more of that on what this looks like tomorrow. Also, we have the equal equivalence assumption. Make sure the spread around the line is nearly constant. Often it's better to look at the residuals plot. Be alert for a fan shape or other tendencies for the variation to grow or shrink in one part of the scatter plot. Meaning, I have a line, my regression line is here. It should be fairly consistent along that line. I don't want to see something that's like, go away, like this. This is what it means by like a fan. It's small residuals here and then they increase, or vice versa. I could have a fan, large residuals out here and then it decreases. So we don't want any of this. We want it to be fairly consistent. And then the normality assumption. Does the histogram of the residuals look normal and contains no outliers? So we're going to actually have to plot the residuals and look at the histogram of that data. So lots of new conditions. Let's see if we can verify those with this example. Look at the moon with binoculars or a telescope, and you'll see craters formed by thousands of impacts. The Earth, being larger, has been hit even more often. Meteor Crater in Arizona, I've been there, it's pretty cool. You should go check it out if you ever get the chance. A little bit out of the way, about like an hour drive out of a normal road. Was the first recognized impact crater. It was identified as such only in the 1920s. With the help of a satellite image, and more craters have been identified. Now more than 180 are known. These, of course, are only a small sample of all impacts the Earth has experienced. Only 25% of the Earth's surface is land, and many craters have been covered or eroded away. Astronomers have recognized a roughly 35 million year cycle in frequency of cratering, although the cause of this cycle is not fully understood. Here's a scatter plot of the known impact craters from the most recent 35 million years. We've taken logs of both age and millions of years ago and diameter to make a relationship simpler. All right, so remember when we did this? Who, what, when, where, why? The who, I'm looking at my craters. What am I studying? The diameter and age. And these units. When? Past 35 million years. Where is going to be worldwide. And wide. This is for a scientific study. Question. Are the assumptions and conditions satisfied for a fitting and linear regression model to these data? So first up, straight enough condition. Let me look at my model here. Would you say this is straight enough? Yeah, right? I see kind of a linear form going on here. Remember, we don't want no U's or no any other kind of lines going on. Looks fairly linear. Next, independent. Randomization. Well, I'm not exactly randomizing my craters. am I? I'm finding the ones that I could find and I'm putting them down. So it's not exactly randomized. Random residuals condition. Looking at the residuals for evidence of patterns, trends, or clumping. I don't exactly have my line yet, but let's say the line fits pretty much here. Do I see anything out of the norm as far as my residuals? No, they look fairly equal a little bit. I do see a little outliers here, but we'll examine that in this part. Looks okay. I just have a question on randomization. Equal variance assumption. Make sure the spread around the line is nearly constant. So if this is my true line, do they look about equal? I say for the most part, these are kind of in question, right? I'm a little concerned about those. But again, for the most part, looks like there's equal variances here. Again, assuming this is my line. I don't see too much of a fanning going on. But the variances is small and then just blows up, gets bigger across. So that one's okay. And normality. Does the histogram of the residuals look normal and contains no outliers? So here's my residual. What do you think? Does it look normal?
No.
It's a little off, right? It's a little skewed. I don't see any outliers, so that's good. But, it's a little off there. I may have to put that in my report. Right? Notice that my residual histogram is a little bit skewed. It's not normal, doesn't fit the normal there. Oops. So, yes, we said the scatter plot is straight enough. Independence, the size of impacts are likely to be independent from one another. This is what we had crossed off, randomization. These are only known craters and many different from others that may have disappeared or not yet found. I'll be careful not to generalize my conclusions too broadly, and all the other ones checked off. Now note with this one, the book checked this one off. A histogram suggests a bit of a skewness in the distribution of residuals. There are no violations severe enough to stop my regression, but I'll be cautious about my conclusions. So they're saying this is skewed, but not enough for me to just stop my testing altogether. So they will continue with this, and we'll continue with that tomorrow. Like I mentioned, we're going to look at two types of tests here. The test for regression slope. When the assumptions are satisfied, we can perform a test for the slope coefficient. We usually test the null hypothesis that the true value of the slope is 0 against the alternative that is not 0. So our null with this is going to be it's 0, and our alternative is not 0. A 0 slope would indicate a complete absence of a linear relationship between y and x. And as you probably could guess, our calculator does have linear regression t-test, stat test f. And then we also could test the confidence interval. When the assumptions are satisfied, we find a confidence interval for the slope parameter of, there you go, the critical value t at n minus 2 depends on the confidence level specified and the student's t-model with a n minus 2 degrees of freedom. So note how we're going to calculate our degrees of freedom here. It is going to be our n minus 2. And again, to find our confidence interval, we're going to use a calculator, and it is in G. Now for today, let's review on finding the regression line and plotting the regression. So I have this data table. First thing I want to do is plot this data table out. What does the data look like? So go in your calculator, go to Stat Edit, and enter this value in your calculator. Now note, there are different ones here. So I have one for 12,000 and one for 10,995. So make sure you type that in correctly. So Stat Edit, what I mean is you should have two ones here. Two ones for 12,000, another one for 10,995. 1, 2, 2 3s. So enter this data. Okay. So your data should have been entered into the table now. Now let's plot to see what this looks like. So go to second y equals, stat plot, and we'll want to turn this plot on. So hit enter, turn it on. We'll keep it as a dot plot, That's 1 and 2. And before you hit graph, hit zoom. So make sure your stat plot's turned on. Zoom and go down to zoom stats. Remember, that makes a nice, neat graph for me. Bam! That's what everybody has. So this is what you're going to do to enter in your data to see if it meets certain conditions. Like, would you say this is nearly straight enough? Yeah, looks pretty linear. Would you say this is a negative or positive correlation?
Negative.
Looks negative, but if you didn't know, now let's try to calculate what the regression line or the line of best fit is. So next, as you see here, calculate the regression line. We're going to, go back. We're going to go to stats, calculate, and skip number 4. That's more algebra. I always wondered why they had this linear regression here where A is first and then X is second, because that's not standard format, but it's for stats. Because for whatever reason, stats wants to be different and they want to write it in this context, where the X value variable is water vapor. All right. So let's 1 and 2. Now wait, before you hit calculate, store my regression equation. This is pretty important because what this does is this will put it in your y equals so that you can graph it. Now, I want to graph it in y1 here. So I need to put y1 in here. How do you pull it off is go to vars, go to yvars. Yes, it's very hidden in there. Function, and there's your y's, y1. So when it calculates my regression line, it's going to give me that calculation and it's going to store it in my y equals for me. That way I don't have to type it all in, or you could just type it on it. But you'll see some of these look pretty ugly to type in. Bam! Now if you didn't see that it was a negative type of slope, you'll see it now. Your b is what? Negative. I have a negative slope here with my x. So my regression line is a of 12,130.6 plus negative 904 x. And if I were to go into y equals, notice how it put that there for me. If I go to graph, there is my regression line. Cool. So let's see, what other assumptions will it meet? I don't see much. I see the variance is about equal, right? I don't see any outliers here or any large spreads. I don't see any kind of trend where it gets small and then fans out, or large and then it gets increases, so that looks fine. Overall, I'll say this meets all conditions. I still need to graph the histogram of the residuals, which we'll do that later. So here's how you're going to graph and calculate your regression line. Stats, calculate, number 8. Use this one. You could use 4, but stats wants you to use 8. Plus, my math lab puts it in the format that 8 is in. So we'll stick with that.